So, good evening, all. So, I am audible or not? Can you please tell anyone so that we can start? Am I
Yes,
audible?
ma'am, audible.
Yes, you are audible.
Okay, thank you.
Audible, ma'am, audible.
Yes, yes, thank you. So, hello everyone. Welcome to the live interaction session on advanced machining process instructed by Professor Manas Das from IIT Guwahati and myself Chinmoy Datta, a paper scholar from IIT Madras. So, if anyone have any doubts or queries, you can please use your chat box and put a message on chat box. I will try to solve. So this week, on assignment 2, which will be on abrasive jet machining and abrasive water jet machining. So maybe someone wants to join. Just a minute. Okay. Uh, so can you please mute your mic? Yeah. Okay, so maybe you have some idea on abrasive jet machining process. So basically what happens in abrasive jet machining process, like in AJM process, abrasive particles are made to impinge on the work material at high velocity. Okay, the jet of the abrasive particles, what? I didn't get actually. Can you please repeat this?
नहीं समझ में आता इंग्लिश
Actually, you are not audible.
Ma'am, actually, he is trying to say that he is more comfortable in Hindi than English.
Okay, actually, most of the students are not comfortable in Hindi. That's why, like, so actually, you are having any problem, then you can use your chat box. I'll try to solve, but I have to be like speak in English only. That's what.
No issue, ma'am. You please continue.
Yeah, thank you. So in abrasive jet machining, the jet of abrasive particle is carried by one carrier gas of air. The high velocity that steam of abrasive is generated by converting the pressure energy of the carrier gas or air is to kinetic energy. So that kinetic energy we can say high velocity jet. Okay, so that nozzle directs the abrasive jet in controlled manner. Still someone is arranging. Okay. So that nozzle directs the abrasive jet in a controlled manner onto the work material. So that distance between that nozzle and workpiece and the impingement angle can be set like we desire how much length we have to set, we can set the standoff distance. Say for zero point 0.5 to 15 mm will be the optimum distance for that standoff distance, that from tool to workpiece distance. Okay, so that then the high velocity abrasive particles remove the material by micro cutting action. That is, we can tell brittle fracture on the work material. So then that abrasive jet machining process, the abrasive particles of around 50 micrometer, like grit size, would impinge on the work material at velocity, we can say from 150 to 300 meter per second from a nozzle. So at zero point 0.5 mm with a standoff distance of around 2 mm. So that kinetic energy of the abrasive particles would be like sufficient to provide that material removal due to the brittle fracture of the workpiece, like, or even say we can say micro cutting by the abrasives. Okay, so the equipments we can say, like, or the parts of that abrasive jet machining, you can see in the figure itself, like that gas supply, vibrator, pressure regulator, filter, power and supply mixture, foot control valve, hand holder, exhaust nozzle, workpiece, and that workpiece will obviously be there. So that in AGM, air is compressed in a air compressor, and compressed air at a pressure of around 5 bar is used as a carrier gas. Okay, so that gases like which can be used as carbon dioxide, nitrogen can also like those are used as mainly carrier gas, which may directly be issued from a gas cylinder. This gas cylinder you can see in the figure, right? So generally that oxygen is not used as carrier gas. So that first like in that gas is first passed through a pressure regulator to obtain the desired working pressure. So that gas is then passed through an air dryer to remove like residual water which are there. That residual water vapor it removes or it dries. To remove the oil vapor or particulate contaminant, that same gas is passed through the series of filters. That carrier gas enters closed chamber, which we can say a mixing chamber also. That mixer you can say, see, right, that mixture chamber, thus it works. That mass flow rate of abrasive entering that chamber depends on the amplitude of vibration of the sieve and its frequency. The abrasive particles are then carried by the carrier gas to the machining process. So their electromagnetic or like electromagnetic action occurs on and off valve is there. So that foot control valve, that works in such a manner that electromagnetic effect will occur. So in the thus all the parts or instruments of the that abrasive water jet machining works. So the first, we have seen maybe in lectures also the brief introductory about abrasive jet machining and all the process parameters on machining process and the surface finishing. So the first numerical is given as in abrasive jet machining, if jet velocity is 150 meter per second and nozzle diameter is 1.02 millimeter, find out volumetric rate of the carrier gas and the abrasive mixture. So in this numerical, just a minute. Okay, so that nozzle dia is given as 1.02 mm, right? So that cross sectional area, what will be the formula for that? Pi d by 2 whole square, right? So d is given as 1.02 mm. So 1.02 divided by 2 whole square. You can get the value. Can anyone tell? What will be the result for cross sectional area? And also you have to be careful in the units itself, because the unit is given as 1.02 mm. So what?
Ma'am, 1.6028.
Okay.
I'm 0.816 something.
Okay, we have to convert. Yeah, we have to convert it into centimeter itself, because the results like we need in centimeter cube per second. So we have to convert it into mm. So maybe 10 to the power minus 2. We have to convert it to centimeter square. So then we'll get the cross sectional area, right? Then find out volumetric rate of the carrier gas. What is the jet velocity is given as 150 meter per second. So what will be the volumetric rate? Z velocity into cross sectional area, that is 150 meter per second is there. So 150 into 100 centimeter per second into that cross section area you are getting. So maybe you are getting some value like 125.5 something. Just check it. So this value is close to that option 1, 123. So everyone has solved this question, right? It's very simple. Like cross sectional area you have to find out first. And what is the cross sectional area? Pi divided to whole square. So you have to convert this whole that unit into centimeter square. Then the jet velocity is given already 150 meter per second. So you have to convert it into also centimeter per second. Then if you multiply cross sectional area into jet velocity, then you will get that volumetric rate of that carrier gas and abrasive mixture. Okay. So shall we move to another part? So that second question is given as, with increasing abrasive flow rate in AWJM, depth of cut. So let me tell you that abrasive water jet machining, brief introduction on abrasive water jet machining. So that you can see that figure, right? The parts of abrasive water jet machining are that reservoir, pump, intensifier. Someone wants to join actually. Just a minute, sorry. So in the abrasive water jet machining, we have seen the parts as reservoir, pump, intensifier, accumulator, controls, hydraulic unit, valve, abrasive tank, abrasive jet, water jet, and drain and catcher. Okay, so every part is having some working principle on that whole machining part. So the reservoir, which works like really. So that reservoir acts as a basic part of like storing water, and the water that is sent to all other parts of the system when it's required. So in that reservoir water tank, water actually is stored. That then comes to the hydraulic pump. Actually, that hydraulic pump acts as a mediator between that reservoir and an intensifier. So what it does, like it sucks the water from the reservoir and sends it to the intensifier. In that intensifier, so what is the working principle of intensifier? Like intensifier is used to increase the pressure of the water. Then that will get the high pressure water. So that after that it goes to the accumulator. So accumulator stores that water temporarily and supplies water whenever it's required, like in system when sometimes there is pressure drop, or say we can say sometimes high pressure water is required, then only that accumulator supplies that water. Then it goes to the control valve that control the pressure of like pressure of the water and also the direction of the water. We can say it regulates the flow of the water itself. So that flow regulator, which it does like regulates the flow of water which is arrived from control valve and send the water to that nozzle. Okay, so that abrasive tank is there where like abrasives are stored. See, water is sufficient. Water can cut the like water can machine that surfaces, but just a minute, someone wants to join. Water can mean like primarily water can cut the like machine the surfaces, but only water is not sufficient for faster rate of machining. That's why abrasive actually is used along with the water. So in abrasive tank, abrasives are stored, say L2O3 sand or SiO2, every like other particles also are there as which are used as abrasives. Okay, so from abrasive tanks it goes to like mixing chamber where water and abrasives are mixed. So it's like if they are in a ratio that 70% of water and 30% of abrasives are mixed together in mixing chamber. So that then comes to that nozzle. So here like high pressure water is converted to that kinetic energy, like kinetic energy, then we can say kinetic energy increases when like nozzle diameter or nozzle area decreases. So that high kinetic energy water like along with that abrasive particles impinge that surfaces for machining purpose or for cutting the material. Okay, so then drain system is also there. Here we can say the drain and catcher. So it collects the water which coming back from the work region, and it what it does, it supplies back to the reservoir. So that's how like abrasive water jet machining process is working. So the question is given as with increasing abrasive flow rate in AWJM, depth of cut increases first, but achieving optimum value decreases. So here the figure is given, right? So from figure itself, you can predict that with increasing abrasive flow rate, how a depth of cut will react on that flow rate, abrasive flow rate. So you can tell from the figure itself what will be the answer, right answer for this.
Increases.
You just refer the figure well, then you can see like it will be increasing or it will be increases first, then it will be decreasing.
Yes, it's increasing, then it's coming down.
Yes. So let me tell you that reason for this actually. So just a minute. So as from the figure itself, you are seeing like that it increases first. When it reaches to the optimum value, then it decreases. So what happens, like in abrasive, size varies, like finer abrasives does shallow is required for shallow depth of cut in the machining purpose, and the coarse particle abrasive particles results in that like high depth of cut. So as well that at depth of cut increases, that MRR also will be increases. So when that abrasive flow rate like increases, depth of cut firstly increases, then after reaching that optimum level it start decreasing because more abrasive particles will be there, then they will start colliding each other, so they will collide with each other, and then they will like occur agglomeration in that part, in that region. So that's why they are not good even for that machining purpose itself. So that's what, like that's the reason that after reaching one optimum level they are start decreasing in depth of cut. Okay, so moving to the next question. In abrasive water jet machining, increase in traverse rate results in. So how depth of cut is like how traverse rate is varying with abrasive water jet in abrasive water jet machining, how depth of cut is varying with traverse rate. So actually basically what is the traverse rate we are like saying as traverse rate is the that relative motion between that abrasive water jet and workpiece. So that is actually achieved by that moving the abrasive water jet or workpiece. Okay, so that depth of cut actually basically decreases with an increase in traverse rate. So that like which like within in the range maybe in 10 millimeter per second basically. So that overcut decreases with increase in traverse rate. So we can say that in when the traverse rate increases, that depth of cut will be decreasing. So the option will be lower depth of cut. Okay. So
Yes.
that yeah. So that next question is in abrasive water jet machining, increase in standoff distance results in. So from the figure itself, you can say right. What will be the answer? Right answer for that? Like increase in standoff distance results in
Lower depth of cut.
Lower distance.
yeah
Lower depth of cut.
yeah.
Lower depth of cut.
Yeah, it's true. Actually, that standoff distance when increases, that depth decreases actually. So what it occurs like rebound of particles and loss of energy that gives shallower depth of cut. So that beyond that upper level of SOD, that actually that cutting will not take place in like reality. So we can say that smaller SOD means that deeper depth of cut and higher MRR. Okay. So moving to the next part, abrasive jet machining is best suited to machine. It's actually abrasive water jet machining process machines brittle materials as well as soft materials and heat sensitive materials as well. So the answer will be all of the above actually. So that next part, one numerical is there. So that is during abrasive jet machining. It's from abrasive jet machining process. So during abrasive jet machining, the mixing ratio used is zero point 0.3. So calculate mass ratio if the ratio of density of abrasive and density carrier gas is equal to 20. Just a minute. So here is that numerical. So in that like mixing ratio is given as 0.3, right? So what is mixing ratio? Mixing ratio equals to volumetric flow rate of abrasive particle divided by volumetric flow rate of carrier gas. Okay. So and that what is given as mass ratio. So mass ratio also, let's say alpha equals to abrasive mass flow rate by combined mass flow rate of abrasive and carrier gas. So that mixing ratio is the ratio of volumetric flow rate of abrasive divided by volumetric flow rate of carrier gas, and mass ratio is the ratio of abrasive mass flow rate to that combined mass flow rate of abrasives and carrier gas. Okay, so from this that mixing ratio we can define as MR. Just a minute. Someone wants to join. So mixing ratio MR we can also MR we can say VA by VG. Okay, volumetric flow rate of abrasive divided by volumetric flow rate of carrier gas. And alpha we can write as MA by MA plus G, because abrasive mass flow rate divided by combined. So MA plus G I am denoting. So 1 by alpha we can write as 1 by alpha we can okay, I'll write it here. 1 by alpha equals to that rho A BA plus rho G VG divided by rho A VA. Okay, so actually basically alpha equals to MA. MA means that rho into VA divided by rho into VA plus rho G into VG. Okay, then we'll get from here like 1 if we subvert this rho A VA divided by rho A VA. So we'll get 1 plus rho G VG by rho G VG by rho A VA. Okay. So can someone please mute your mic actually? Please mute your mic.
Electrical.
SS Kumar, it's your mic only.
You please mute your mic actually.
SS Kumar, for you only telling.
So anyway, like that 1 plus we are getting rho G VG by rho A VA. So that we can say rho G we can write it as rho G by rho A into VG by VA. Okay. So then we'll get 1 plus rho G by VG, which is that it's given as density mass ratio. If the ratio of density of abrasive and density of carrier gas is equals to 20, so it's given, right, that ratio of abrasive, that is rho A, and that density of carrier gas, that is rho G. So rho G by rho A by rho G is given as 20. So rho G by rho A will be 1 by 20. Okay, into Vg by Va. So in Vg by Va also the mixing ratio is given. So what is the mixing ratio? That is volumetric flow rate of abrasive divided by volumetric flow rate of carrier gas. Okay. So it is given as rho A by rho G is Va by Vg is given as 0.3. So Vg by Va will be it will be 1 by 0.3. So if we solve this, we will be getting 1 by alpha how much? You just solve and tell me 1 plus 1 by 20 into 1 by 0.3. How much we will get? We'll get 7 by 6 I guess. Is it correct? Seven by six we are getting as 1 by alpha. But our requirement is alpha, right? That mass ratio. So alpha will be 6 by 7, which is 0.856. So it's nearer to that 0.86, that is option B. That is option B. So is it coming or not? It's coming as 0.856, right?
7 by 6, ma'am. It's almost near.
Yes. That 1 by alpha actually it's coming as 7 by 6. Then we have
Yes,
to
ma'am.
calculate alpha, then it will be coming as 0.856. So it is nearer to that option B, 0.86. So the correct answer will be option B. So going to that next question. See, maybe you can get some questions such as like catcher, which is used in AWJM, AJM, or USM in which process? So, where we are using catcher? So, in abrasive water jet machining only we are using catcher. So, why it's used? We have seen in the that parts in abrasive water jet machining part also that how catcher is working. So that once that abrasive jet has been used for machining, like that there may be sufficiently high level of energy, depends on the type of application actually. So that such high energy abrasive water jet, it actually needs to be contained before they damage any part. Okay, that's why that's the reason actually catcher is used to absorb that residual energy of that AWJ, that is abrasive water jet machining process, and dissipate that same residual energy. Okay, so the right answer will be to absorb the residual energy and dissipate the same. Okay, because we have seen in that parts also, right, where drain and catcher is given. So what it does, like it actually avoids the damage of any part of that machine. So what it does, it absorbs that residual energy of abrasive water jet machining and then dissipate the same residual energy. Okay, actually there are different type of catchers are used: water basin type, submerged steel balls, and TIB2 plate type. There are different type of catchers are used. You can see the figures also. Is anyone having any question? Yes. Yeah. To absorb the residual energy, most catchers has water and field arrangement. Yeah, it's correct. Okay. So coming to that next question. With increase in abrasive flow rate, from the figure itself you can tell, right, how abrasive flow rates are affecting the time error. So you can tell from the figure itself, right? Yes. M error first increases and then decreases. Do you know the reason of that? Like why first M error increases then decreases? Why actually is this behavior we are seeing, like first M error increasing with abrasive flow rate and then it will decrease with increasing abrasive flow rate?
Because the abrasive,
Because
the abrasives will be worn out now, madam.
yeah, and like we can say, just a minute. So actually what it happens here, like M error like increases only up to a certain level we are seeing in the figure itself of abrasive flow rate. Beyond that optimum level, it will start decreasing. That as that abrasive flow rate increases, the number of abrasive particles that cut the material also increase. So it will increase the M error eventually. But lower abrasive flow rate leads to that lower material removal rate, because due to that less number of cutting edges present in that machining process, and that after that certain level, when it reaches that certain value, abrasive flow velocity actually start decreasing due to that increased mass fraction of abrasives. Just a minute. So that after that certain level, abrasive flow velocity start decreasing due to that increased mass fraction of abrasives, which occurs like reduction in M error, and then that jet is distributed among more number of particles. So that effect actually like is working in that decreasing in that MRR with increasing in abrasive flow rate. So becomes that with that flow rates greater than, we can say that 40 gram per minute, we will see that decreasing nature. But up to that 14 gram per minute approximately, we will see that with increase in abrasive flow rate, MRR will be MRR will be increasing. After that only it starts. So that actually what it happens, like to that conserve that nozzle, that nozzle life, most like operations are performed at 10 to 15, in range of 10 to 14 gram per minute abrasive flow rate only every machining processors are working, because it will save that nozzle life actually. So that's the reason behind that graph actually. So those are the few assignment questions which you can refer to solve these year assignment question actually. Most of the questions I have like I tried to explain what are the numericals, even if they are in previous year NPTEL lectures. So I try to solve you, if you refer those numerical solutions, you can answer these year questions also. And the questions which are there, basic questions, that how process parameters are affecting in M error, how depth of cut and M error are like reacting with process parameters in FWGM and HM, those are also I have discussed. So you can refer to those and you can like solve these year assignments. So that's all for today. So if anyone having any doubt, you can reach to me in my mail ID. I'm like in chat box, I'm writing my mail ID. So I have mentioned my mail ID. So if anyone having any doubts related to that lectures, you can reach to me or you can post a mail to me. I'll try to solve. So if no one have any doubt, so we can close the meeting.
Yes, ma'am.
Okay,
Thank you.
thank you, ma'am. Thank you so much.
Yeah, thanks.
Okay, ma'am. Thank you.
Yeah, thank you.